so that leads us into something called common response. For common response, what you have to do is you have to beware the lurking variable. The observed association between two variables can sometimes be due to a third variable. So in other words, both x and y may be changing in response to changes in z instead of in response to each other. So consider this fact. Students who are smart and who have learned a lot tend to have both high SAT scores and high college grades. This positive correlation is explained by the common response to the student's ability and their knowledge. So you can't say that high SAT scores cause high college grades. Instead, you would say that their ability causes both of those things. That's an example of common response. So a lurking variable is a variable that's not included in a study, and it may influence the interpretation of the relationships among the variables. Right? That's the definition of a lurking variable. A variable that's not included in a study, but which might influence the interpretation of the relationships. A lurking variable is sometimes referred to as a common response. So another example, if you were to pick any measure of technological modernity, so in other words, number of TVs per capita and life expectancy, you will clearly see an association. Countries with fewer TVs have lower life expectancy. Now, would you say that the number of TVs causes you to live longer? No. You would say there are lurking variables. Countries who are rich countries, tend to have a lot of TVs, and they also tend to live longer. And it's not the TVs that's causing long life, it's the richness of the countries. So that's an example of a common response. Here's an example. Sleeping with one's shoes on is strongly correlated with waking up with a headache. So can we say that sleeping with one's shoes on causes headaches? Well, no. Anyone who's been to college might be able to explain that. A more plausible explanation is that both are caused by a third factor, in this case going to bed drunk, which thereby gives rise to a correlation. And another example, young children who sleep with a light on are much more likely to develop myopia later in life. So does this mean that sleeping with the lights on is causing the myopia? No. Actually, this was a real study that was done by the University of Pennsylvania in 1999, and they received a lot of coverage. However, a later study showed that a later study did not find that infants sleeping with a light on caused the development of myopia. However, it did find a strong link between parental myopia and the development of child myopia, noting that myopic parents were more likely to leave a light on in their children's bedrooms. So in this case, the lights didn't cause the myopia, it was the parental myopia. The parental myopia caused them to leave a light on, and it also caused their kids to develop myopia. Genetics. As ice cream sales increase, the rate of drowning deaths increases sharply. So does ice cream cause drowning? Well, no. The aforementioned example fails to recognize the importance of time. Ice cream is sold in the summer months at a much greater rate because it's hot outside. During the summer months, people are going to the beach, going swimming. Therefore, the increased drowning deaths are simply caused by more exposure to the water activities. So it's the heat, it's the time of year that's driving both things. It's driving the ice cream sales, it's also driving the number of deaths. That's an example of common response. With a confounding variable, the effect of the confounding variable cannot be separated from the effects of the explanatory. So here's an example. Whether a person regularly attends religious services and how long the person lives. Well, many studies have found that people who are active in their religion live longer than non-religious people. But people who attend church or mosque or synagogue also take better care of themselves than non-attenders. They're less likely to smoke, they're more likely to exercise, they're less likely to be overweight. The effects of these good habits are confounded with the effects of attending religious services. You can't tell whether it's the religious services that's affecting the person's lifespan or if it's all these other things. So all these other things that are the confounding variables. Okay, the number of years of education a worker has and the worker's income. Well, once again, it's likely that more education is a cause of higher income. Right? Many highly paid professions require advanced education. However, confounding is also present. People who have high ability and come from prosperous homes are more likely to get many years of education than people who are less able or poorer. And of course, there are people who start out able and rich. They're more likely to have high earnings even without much education because they're starting off from such a good spot. So we really can't say how much the higher income of well-educated people is actually caused by their education. So, suppose we wish to test a new deodorant against one that is currently on the market. Here's what we would do. First, we would separate them into two groups. Alright, so we have blues and pinks. One group will be assigned to treatment A and the other group to treatment B, and this is where the randomization comes in. Okay, once they're all assigned, randomly assigned to the different groups, the treatment in the group are confounded. So notice this example. In this example, we have confounding variables. And the confounding variable is all the blues got treatment A, all the pinks got treatment B. So we don't know whether it's the color that's causing the response variable or whether it's the deodorant. Alright, so this is a bad example. Confounding will not appear or will not occur in a completely randomized design. So if you're doing your experiment correctly, there should not be any confounding. Alright, so here, an article from USA Today reports the number of victims of violent crimes per 1,000 people. 51 victims have never been married, 42 are divorced, 13 are married, and 8 are widowed. Is this an experiment? Why or why not? No, it's not an experiment because there's no treatment being imposed. What are potential confounding variables? Age. Younger people are more at risk to be victims of violent crimes. Example 5. 4 new word processing programs are to be compared by measuring the speed with which standard tasks can be completed. 100 volunteers are randomly assigned to one of the 4 programs and their speeds are measured. Is this an experiment? Yes, because a treatment is being imposed. Right? We are randomly assigning them to one of 4 programs and then measuring their speeds. What type of design is this? Well, they're being randomly assigned, so it's completely randomized. What are the factors and what are the levels? Well, there's one factor. There's a word processing program with 4 different levels, and the response variable is the speed at which they are typing. Okay, continue with example 5. Is there a potential confounding variable? No. Completely randomized designs have no confounding. Can we improve it? Certainly. We could do a block design where each person uses each program in random order. So we could do a matched pairs where every person does each program and then we'd be able to compare their speed within each program. Randomization reduces bias. Just remember that. It reduces bias by spreading any uncontrolled confounding variables evenly throughout the treatment groups. Bias, remember, is a systematic error in measuring the estimate. If you're making the same mistake every time, then there's some bias there. Blocking will help reduce variability. Another way to reduce variability is with sample size. Larger samples produce statistics with less variability. Okay, so randomization reduces bias. Blocking helps to reduce variability. And variability is controlled by sample size. So here we have 4 different dartboards. The upper left, that's an example of high bias and high variability. It's high variability because it's very spread out. It's high bias because they're consistently missing to the left. The next one, upper right hand corner, that's high bias but low variability. Low variability because it's very tightly grouped. High bias because they're consistently missing too high. Bottom left, low bias and low variability, or high variability. It's low bias because it's all spread out. They're not consistently missing in any one direction. But it's high variability because it's too spread out. The last example is what you want. You want low bias, right, where they're all right in the middle, and low variability, where they're all tightly grouped. That's the ideal. That's what you're shooting for. Now, an important definition, super important, statistically significant. An observed effect that is so large that it would rarely occur by chance is called statistically significant. This is a phrase that you're going to hear us repeating over and over and over again for the rest of the year. So make sure you write this down and highlight it and circle it and put stars next to it. An observed effect so large that it would rarely occur by chance. We call that statistically significant.
That's all, folks.